Swayam Prabha. Digital India. Educated India.
So, welcome all of you for the first chapter on mechanics of sheet metal forming course, that is introduction to sheet forming process. So, in today's class we are going to see the first chapter, okay, and it will continue for the next class also. Okay. So, now this first chapter is divided into actually two parts. One is basically introduction to the sheet forming process, and then we will see an important aspect of material testing, that is tension test. Okay. So, let us go to the introduction of sheet metal forming process. As you all are aware of the fact that metal forming operations can be divided into two categories mainly. One is bulk forming process, the other one is sheet forming process, and this course is predominantly on sheet metal forming process, mainly the mechanics part. Okay. So, when it comes to introduction, okay, so I have given three important points in the slide. Okay. So, we are all aware of the fact that we have hot rolled strip and cold rolled strip sheets, okay, in the form of sheets. Okay. So, they are basically deformed, plastically deformed, and certain shapes are made, okay, to make useful components in you can see automotive industries, household appliances, building items, aerospace structures, and commonly used food and drink cans, and variety of other known products. Okay. So, the sheets are actually deformed using several sheet forming process to make a particular shape. Permanent shape changes allowed in that. Okay. Generally, we want these days a strong strength to weight ratio. So, all parts are manufactured, material selection and the process optimization, everything is done keeping in mind that strength to weight ratio is going to be important. Okay. So, what are the common sheet forming process? Of course, you all know that bulk forming process are of different types. Say for example, forging, extrusion, rolling. Okay. So, wire drawing, that we generally study in manufacturing technology courses. Similarly, sheet forming process also can be divided into several types, and it also depends on what type of components you are going to make. For example, blanking and piercing, okay, bending, deep drawing, okay, and there are other sheet forming process, okay, like roll forming. Okay. So, we are speaking about sheet, it could be tubes also, tube forming is also possible to make certain components. Okay. So, to start with, we are going to briefly see some typical examples of that. Say for a first instance, you can take blanking and piercing. Okay. A schematic is given here in this diagram, you can see. Okay. So, you have a sheet here, okay, and the sheet is actually clamped using blank holder. Okay. So, the clamp, it's called clamp. Okay. So, the sheet is held on one side and the other side is free to deform. Okay. So, and you have a punch, or you call it as a die, that's called cutting die. The cutting die is slightly different from other dies which we use in other sheet forming process. Here the main purpose of die is actually to cut the sheet. Okay. As you see in this diagram, so the sheet is undergoing severe plastic deformation in this region, and you will see that at one particular stage fracture is going to get developed, and these two regions will get separated. Okay. And this part will actually come down, okay, and it will be separated from this part of the sheet. Okay. So, generally this operation is done in presses, okay, and additional blanking may be required later to remove extra material and punch holes. Okay. That is the entire process. And if you closely look at this, it's actually a complex process of plastic shearing and fracture. Okay. So, you need to have plastic deformation in this clearance region. This clearance is also very important in this case, and this particular parameter clearance is going to be generally designed in such a way that appropriate cutting is actually done. Okay, and you will see that this edge region, that means this region which is undergoing deformation, okay, will undergo localized hardening. Okay, so that's very important, and this shearing as such is not going to make a shaped component, rather it is going to be helpful for sizing. Okay. So next important one is called as bending. So this bending is a very common process used for making several sheet components. Okay. For example, you can have household utensils, washing machine parts, like that. The components are actually bent at certain locations, and other than that several other forming process are also available to make that component. Okay. So this schematic is actually a straight line bend. Okay. So that means this portion was initially, you can see horizontal in nature, and we will see in the next slide. Okay, there are presses which is used to bend it to about 90 degree, you can imagine. Okay, so the angle is about 90 degree here. Okay, so and the bending is done in one line. Okay, so that's why it's called straight line bend. Okay, it's a basic plastic deformation process. So and the plastic deformation happens here only in this bend zone, you can imagine. Okay, this portion and this portion are not going to have any plastic deformation. Okay, it's unaffected region. Okay, but this type of bending process will also have some problems. For instance, they will have elastic spring back, which we are going to discuss elaborately little later part of this course. But the brief idea here is, suppose this angle is 90 degree. So you can imagine that after we think that bending is over, then we remove load. So this will not be 90 degree, this will be rather a different angle. Okay, so that change in dimension is because of we can say it as elastic spring back. Okay, so this spring back has to be minimized. There are several methods that people follow in this subject. Okay, we will see how to model this elastic spring back in a very simplest fashion. And the main problem is, if you allow spring back, then assembly of these parts with respect to other parts will be a difficult task. So what are the different bending methods? These are some schematic I have given here, A, B, C, D. Okay, so you can imagine that bending is done using 4 different processes. Okay, the A part is going to be little folding type of thing. Okay, you can hold the sheet in this particular region, and okay, the sheet is actually clamped here, and it is rotated in this direction, or of course you can rotate it in the opposite direction also, and you can make a sheet of like this. Sheet will be bent like this. Okay, so to get a previous one, this type of L-shaped bending is possible. Okay, so there are other ways of bending. This is another example. The B part is called V die bending. Okay, where you have a die and there is a groove. Okay, V groove. Okay, on which you have a sheet, and the punches are of same size of the V die. Okay, and you can see that the punch is going to move down, and it is going to touch the flat sheet, and further you move down, it will be bent like this. Okay, so once you remove the punch, okay, it has to have that particular shape. Okay, what do you need of a desired dimension? For example, fully bent sheet should have this type of bent section, isn't it? So that is the another bending process. Okay, so roll forming, as I was telling you, so roll forming is another method where you can see that rolls are used. These are all actually rolls, and a sheet is kept in between, and the roll is actually going to roll, and then it's going to create this type of bending. Okay, so you can have channel sections. Okay, like for example, wide panels like roofing sheet or intricate channel sections can be produced using roll forming machines, and you can have numerous sets of rolls successfully bend the sheet. Okay, it is just not in one section. You can have different sets of rolls, and it getting continuously bent. Okay, to make any channel section. This D type is called flanging, and it is a relatively well known method. Okay, like in piercing you have a cutting die, right? Instead of that you have just a flanging tool, and it is not going to cut the portion in the bend region, it is just going to bend it. Okay, so it's not going to really shear cut the sheet, rather it's just going to bend it, and you will see that finally you are going to make a L-shaped component like this. Okay, so basically the flange tool is going to move down in this way, and is going to push the sheet towards the die, which is kept stationary here. Okay, and once you release the flanging tool, we want this 90 degree shape, but then there will be some slight change in the angle, which is what I was referring to as a sheet spring back, which we will discuss elaborately later on. Section bending. Section bending is a little complex in nature when compared to other simple process we discussed before. Okay, and here as given in the schematic, you can see it is basically like a channel, okay, starting from here to here, and the channel is also of a complex shape that you can see that there is a significant height of deformation given here, and there are a lot of problems here because you will see that there is a bending here and there is bending here, okay, and the edge region is going to undergo deformation, okay, and you can also see that as referred to the schematic, there is a small fracture here and there is a lot of wrinkles here, okay, and because of that you will see that this height is going to be lesser than this particular height. Okay, so the sheet is curved into a more intricate shape. Okay, it shows the schematic of the process. The flange of the channel is strained and many split at the left end of the portion, and legs height h will drop. That is what I was telling you. Okay, so you are going to be little bit careful in this type of defects. Okay, wrinkling and an increase in flange height, okay, are possible on the right hand side. Okay, so here fracture is possible, here wrinkling is possible. Because of that, your your height of deformation here and here are going to be slightly different. So one has to be careful, okay, when you deform this kind of intricate shapes using bending. So there are other sheet forming operations, like a famous one is stretching. Okay, as the name says. So the schematic also shows that as an example. You can see this is the actual sheet, the upper part, okay, and you can see the setup here in B part, okay, where the same sheet is actually clamped between the die and the blank holder. I hope you all are aware of the fact that in sheet forming you need tools, for example die and blank holder and punch, to deform the sheet plastically. Okay, so die is kept on top and blank holder is going to clamp the sheet onto the die, and you have friction between at the interfaces here on both the sides. Okay, and you can imagine that in the top view it's going to be of this particular type of deformation. So punch is going to touch the sheet first, and further displacement in the punch will deform the sheet in this fashion, and you can see A part is nicely going to give a section view of how the deformation is going to be. Okay, the punch is pushed into the sheet. Okay, now one important point here is the sheet most often it is not going to be drawn in. This movement is generally restricted here because of the clamping force and your friction, interface friction. So what happens is there is going to be significant tensile forces that are generated at the center forces, or at the center region. Okay, these are the forces that cause deformation, and contact stress between the punch and the sheet is very much lower than that of generally yield strength of the sheet. That's what generally people say. So this stretching, okay, we are going to discuss elaborately in further chapters. Can also be used as a material testing method. Okay, so you can use this as a formability test. Okay, so to see what is this particular, let us say what is the height of deformation. Okay, let us say this is height. Okay, so let us say this is your, for example, it is your height. For example, so what is the height of deformation you can have at which you have a fracture in this location. Okay, that can be used as a measure for sheet formability. Okay, so that can be well discussed with respect to this figure as h, let us say, this height of forming. Okay, so more complex details going to come in future, but I am just giving you an idea here. And then hole extrusion is another sheet forming process. It is also called as hole stretching. So the same stretching operation, you can imagine that a sheet has got a hole at the center. Okay, there is a hole at the center and there is a punch. Okay, there are standard methods for that. We are not going to discuss about that, but okay, the punch is going to deform the sheet, but where hole is located. Okay, so then you will have this kind of deformation. Okay, this is the height at which to which the hole is deformed. Okay, so a small hole is made. Okay, a small hole means the hole should be diameter should be lesser than that of the punch diameter. Is initially bored into the sheet. The punch can then be forced into the sheet to raise the lip. Lip means this particular region. Okay, lip. So now what will happen? This whole edge will undergo a typical deformation process, and the material should not fail before it reaches one particular height, and especially failure will happen mainly in the edges. So you have to be a little bit careful in that. So your hole stretching, okay, or extrusion of punched hole is very important to understand how hole is going to deform when you go for actual sheet forming process. Okay, depending on this, one can select the the material responsible for making a good material which is be useful for making that kind of components. So, I have just written here that the splitting will limit the height of extrusion will be appreciated. Okay. So, the larger the height it will be better, but at the same time you should be able to make the the whole stretching operation without any problem. Okay. That means a fracture should not happen at the edge region. So, this stamping or draw die forming is another method like deep drawing, which you are going to see in the next slide. So, here you will see that stamping is generally a shallow deformation process. It is also called as draw drying form. Okay. So, draw dry forming. So, I have given you some schematic here. You can see that it is a shallow drawn part, okay, not like your deep drawn cup. It is a shallow drawn cup, okay, or a pan, something like that you can imagine. So, the sheet is kept on the above the die. You can see that here it is a die and there is a punch. Let us say punch is shown here in the B part and it is going to deform the sheet, and the sheet is clamped actually between the blank holder and the die ring. So, the idea is same as punch stretching previously stated, except material for the component is supplied by allowing the outer edge or flange to draw inwards while being restrained. So, that is the main difference here. That is why I told you in the previous slide that you will see that this movement of sheet in the radial direction is not allowed here. Okay. But on the other hand, you will see that here it is actually allowed. The material can move in this direction, but of course with some restriction. Okay. The restriction is mainly because of holding as well as because of friction. Okay. So, it moves inwards and then you make a component of this particular shape. So, what are the applications? A lot of applications you can see. One is automotive body panels, okay, are created, and there are several stainless steel simple pans are used for many applications. So, they are all made by this type of process. Okay. So, the tools are same. Okay, you have punch, you have a die ring or a you can also call it as a draw ring, and then a blank holder which is used to make this particular component. So, deep drawing is similar to this particular process. Only thing is here the drawing is actually little deeper. Okay. So, you make larger cups, okay, like for example you have this soft drinks can. Those things are made by components are made by a deep drawing process. Of course, there are several stages in that. Predominantly it is a deep drawing process, and the tools are going to remain same. So, you have punch, you have die, you have blank holder. So, purpose of blank holder is nothing but holding the sheet, and that is going to lie above the die, and you have a punch which is going to touch the initial sheet, which is kept like this, and then the punch is going to move down and the sheet is going to get deformed in this way, and this movement, radial movement, okay, inward radial movement of sheet is actually permitted. Okay. And you will see this particular example is for partially drawn sheet. That is why you have a cup bottom, a cup wall and a flange region. Okay. So, this portion is called flange region of the sheet, and this is cup wall of the sheet, and this is your cup bottom of the sheet. Okay. So, here of course, when you speak about deep drawing, okay, so the ideal actual aim is basically to make a full cup like this. Okay. There is no flange region here. So, you have to make a full cup in this. So, that means the whole flange region should be converted into a cup wall. Whole flange region should be converted into a cup wall. That is the meaning here. Okay. So, here there are 2 or 3 important parameters other than the sheet material properties itself. One is this clearance, like let us call this as C. The C has to be very important. Okay. If C is less, then something is going to happen, that you will see in next slide. If C is large, then also it will lead to some other problems, defects during deep drawing. So, this clearance should be appropriate. That actually depends on the sheet thickness. Let us say thickness is T naught, initial thickness is T naught, okay, and instantaneous thickness is, let us say, T. Okay. So, this clearance should actually take care of this particular thickness. Let us say, for example, you have 2 mm thick sheet, means the clearance should be slightly larger than this 2 mm thick sheet. That is the way you have to give clearance. There are formula available for that. So, one can look into it. So, now other than that, lubrication is important. So, you have a friction between the punch and the sheet, okay, then you have blank holder and the sheet, okay, and die and the sheet, okay. So, interface friction is going to be important, and that is why we are using lubricants. In the deep drawing chapter later on, we are going to study very briefly about redrawing of sheets. Redrawing means, so this deep drawing is done in several stages. Okay. There are 2 varieties in that we will see later on, but redrawing is also possible. Redrawing means instead of one stage, you make the component in let us say 8 different stages. Again and again and again the material is actually redrawn to make any component. But the principle, the process is going to remain same. So tube drawing is also possible, like I gave an example before that the sheets are raw materials here, but other than that you can also have tube as a raw material, and you can see that this tube, okay, tube means metallic tube, okay, made of aluminum alloy or stainless steel, let us like that, okay, and so those tubes can be deformed on its edges or somewhere in the middle to make certain components or shapes. For example, flaring. Flaring is one way of making some shape change to the material, okay. Tube sinking is possible, tube reduction is possible, like what we have in water cans, no? At one end the diameter is actually reducing, right. So that can be made by your tube reduction, okay. So diameter is actually going to reduce, and that can be made using this type of arrangement, like you have a die and you can see that this diameter is larger when compared to this diameter, okay, and you will get a nice shape change given to this tube like this, okay. So this is also possible in tube drawing. There are several components one can make with this tube drawing operations. Then comes a totally new type of sheet forming process called as fluid forming, or it is famously called as hydroforming. So until now, whatever the sheet forming process we have discussed are predominantly done by you have a punch, you have a die, blank holder, okay, and mostly it is done through these 3 important tools, okay. But instead of rigid tools means the sheet is actually deforming. All other tools, okay, like punch, die and blank holder are actually rigid, okay, they are not going to be deforming at all, okay. Instead of using rigid tools, what people do is they use fluid pressure, okay, as a deformation medium. An example is given here, okay. So you want to make a sheet part like this. This is your sheet, the bottom part is actually sheet or part or component you can say, okay, and there is a die here, okay, this is your die as written here, and you can see that there is a pressure container, it is written as pressure container, which contains a fluid, okay, and you are going to pressurize the fluid in the way it is given, okay, and the fluid pressure is going to deform the sheet, okay, to make this particular shape, okay. So between the fluid and your sheet you can have a diaphragm. Diaphragm is given here, this particular part is actually diaphragm which is given here, okay. So the diaphragm is typically put over the sheet of material and pressurized in a container to make a flat pieces, okay. So the diaphragm is actually going to it will not allow physical contact between your fluid and the sheet, okay. It is going to prevent the contact between fluid and the sheet, okay. So mainly to take care of the other negative effects of fluid onto the sheet, okay. Just to avoid that, okay, you have this diaphragm. At the same time, the diaphragm should not disturb the plastic deformation of the sheet, okay. Special presses are needed here, that is the main thing. So you cannot use a conventional presses used for your sheet forming process, so you need a separate press for this, which can take care of pressurizing the fluid, controlling it, measuring it, all those things are required here. The pressures needed to keep the container closed substantially stronger than those acting on the punch in a draw die, because the pressure to form a sheet in sharp corners can be very high. You will also see that in the initial part of the deformation, okay, you will have deformation other than the corner region, this die corner region, and later on you will see that the pressure is required to push the sheet to take this shape. So this corner filling is going to be very, very important. So in that case you need to have significant pressure acting on it. So here this example is mainly for sheets, right. Similarly, tube hydroforming is also possible, okay. Tube hydroforming is also possible. So we will see one chapter at the end of the course predominantly on tube hydroforming and why it is important for us, okay. So complicated tubular parts for plumb fittings and bicycle frame brackets are heavily dependent on fluid forming, okay. So you can make this kind of plumbing fittings, okay, and bicycle frames, okay. So they are made by this kind of tube hydroforming process, which is generally made by like 2 different processes. Say for example, you make one tube, you make another tube, and then you go for welding at the wherever you want to assemble, okay. So the main advantage here is you avoid post forming process like welding, Okay. So, that is one important advantage of fluid forming or hydroforming. It could be sheet hydroforming or tube hydroforming. Okay. So, just to complete this particular small chapter, coining and ironing. Coining and ironing. Okay. So, of course, coining, as you see in the schematic, okay, there is a sheet and there is a coining tool which has got a slight impression over here, and that impression will be put onto the sheet in this region. Okay. So, it is basically like some sort of shallow plastic deformation that can happen, but that is going to be very, very intricate, okay, because the sheet, as we speak, what we speak is of the order of, let us say, 1 to 2 mm, okay, or maybe 2.5 mm, and you have to give some shape on the in the thickness direction. So, you have to be that shape is going to be little intricate, and finer dimensions have to be captured. Okay. So, that is one important thing when you speak about coining. So, during coining, I will come to ironing after this. Okay. So, during coining, the sheet material is heavily compressed in the through thickness direction to get the desired shape. The through thickness direction means, let us say this is your T thickness. So, in this direction you are actually deformation is given, but within the sheet thickness. That is why intricate shapes are made using this kind of coining. So, now ironing is also another important one process in which through thickness compression is actually going to happen like this. And this is what I was telling you before in deep drawing, that suppose you keep a clearance, okay, this clearance, let us say, you can see this clearance in deep drawing, this clearance we were speaking about, right. This clearance, let us say, is smaller than the sheet thickness. Just for example, I am saying sheet thickness is, let us say, 2 mm, T naught is, let us say, 2 mm, and the clearance is, let us say, just 1.9, 1.8 mm. So, what will happen? This ironing will happen. Okay, ironing will happen. You can see that actually this is your sheet and this is the cup that is formed, okay, with the same punch, and you have ironing die, and you will see that here the sheet, the cup is going to take this clearance, okay, this clearance, this particular clearance dimension it is going to pick up. Okay. So, you will see that the thickness is actually getting reduced while the cup comes out. So, it is just not making of cup with a particular thickness, rather it is going to be specifically designed tool such that you want a particular thickness in the cup wall. Okay. So, you want a particular thickness in the cup wall, then you should go for ironing operation, and you should also note that the thickness here, okay, and thickness here and thickness here, okay, they are not one and the same. Okay. So, I will say that an ironing die that is pushed through a cylindrical cup is slightly smaller than the punch plus the thickness of the metal. This is what I was telling you. Okay. The wall thickness can be decreased by more than half in one pass when numerous dies are used. Okay. So, the wall thickness, the cup wall thickness have to be, want specific cup wall thickness, then one can go for ironing operation. Okay. And that can be done mainly by controlling the clearance, between the clearance, which is nothing but the gap between your die inner and the punch outer. Okay. So, we will briefly see some details about ironing later in the deep drawing chapter. Okay. So, with this I will stop my first introduction to sheet forming operations, okay, which is nothing but chapter 1, you can say. Okay. And we will immediately move on to chapter 2. So, in chapter 1, just to summarize, what did we see is basically some basic sheet forming operations, right from, let us say, your stretching, deep drawing, then you have stamping, okay, then you have simple bending, okay, and different bending operations available, okay, and shearing or blanking where you want to cut the sheet, and then finally we have seen some specialized process like tube drawing, hydroforming, okay, ironing operations like that. So, I think we appreciate the fact that all this forming process involve plastic deformation. Okay. Permanent shape change is given to these raw materials which are in the form of sheets. Okay. So, now let us go to the second chapter, that is nothing but material properties. Specifically, we are going to discuss about a tension test here. Okay. And when we speak about a tension test, I hope all of we are all aware of the fact that there are other material testing methods also. Okay. Say for example, you have a compression test, they are meant for different situations. Okay. Of course, you have tension test, we have studied this in material science book, or maybe material manufacturing technology. Okay. Then you have hardness, then you have fatigue testing, okay, then you have creep. Okay. So, there are several other testing methods available, okay. But with respect to sheets, if you see, if you want to model sheet forming processes, okay, then you need to know how to calculate basic mechanical properties which are generally done by tension test. And this tension test, just to give you a very brief significance, these tension tests are not only used to evaluate the basic mechanical properties of sheets, it also used to select which sheet material is suitable for what type of applications. Okay, say for example, in houses we have stainless steel wash basins. Okay, so stainless steel, like why one need to choose stainless steel for that application is a question. Okay, then it basically connects us to several important requirements. One of that is properties. Okay, so it's a significantly drawn pan, isn't it? So the height of drawing is significant, right? So you need such type of material. So how do you calculate, how do you evaluate, how do you measure that is by doing tensile test and get its properties. So the properties have to cross certain requirements to make that particular component. Okay. So tension test used for that purpose. Okay. So selection of material for one particular application is very important for us. So when we speak about sheet metal forming and tension test, first of all we need to define there is something called as formability. Okay. This formability is a term which is defined along with ductility. So if we know ductility, what is ductility, then we can define formability also. So before deforming the workpiece to a certain desired shape, choosing workpiece material is very critical. This is what I was telling you, which is the first point. Strength, density, stiffness, corrosion resistance are some of the attributes that are most crucial when choosing a sheet material for a workpiece. Correct. So what is the strength? How strong it is? Okay. So what type of density you have? What density you have? How stiff is the material? Whether corrosion resistance is significant or not, that depends on the application it's going to have. Okay. Or some of the attributes or quality that we look into it. Okay. So now in this context, if you want to define formability, we define it like this. A typical definition of formability is this: the ability of a sheet metal workpiece to withstand plastic deformation without being damaged is referred to as formability. Okay. So ability of sheet material to withstand plastic deformation, that we already know because we want to give permanent shape change. So naturally plastic deformation is mandatory without being damaged. Without being damaged means it should not have any instability that is getting developed during the course of deformation. So what is instability, we will see it in a separate chapter, but otherwise you can take it as here as damaged means let us say fracture. Okay, the material should not fracture at all. Okay, that is the main requirement here we have. Okay, so wherever the material fractures, then we say that its useful formability is over, and any shape change that is given to the material before that is going to be helpful for us. Beyond that you cannot give useful shape change to the material. That is the meaning. Okay, so that is why I was telling you in deep drawing that the height of cup that is formed is going to be very important. Okay, and until you make that component, it should not fail anywhere in that cup. Okay, so formability, this is ductility also means in a way it has got the same meaning. Okay, it's the ability of a sheet metal to undergo useful plastic deformation, okay, without being damaged or without being fractured. That is referred to as a formability. Okay, and in this context, the meaning of elastic and plastic deformation. So we will not discuss much on elastic deformation. I think you might have studied this in solid mechanics. Elastic deformation is generally small. Okay, so whenever you do tension test, first of all it has to cross elastic deformation, then you enter into the plasticity part. Okay, this elastic deformation generally small and sometimes can be neglected. Okay, but at some certain situations like spring back, which we will see here, which is nothing but something called as elastic recovery. Okay, wherever spring back occurs, the elastic shape changes the final component shape and it's compatible with incompatible with other mating parts. Okay, so it's going to disturb two things: one, shape change, and is also going to disturb its compatibility with the other mating parts. At that type of situations, the elastic deformation should not be neglected. Otherwise, whenever you go for large plastic deformation, elastic deformation is generally, it can be neglected if it does not have any other problem like this when you go for modeling. So now shape change in sheets permanent shape change in sheets is accompanied by plastic deformation, okay, that is you are going to give permanent shape change to the material. Okay. We have already seen some examples, okay, a cup formed or a shallow drawn cup that is formed by stamping or a simple bending, okay, all involve permanent shape change. So, now when it comes to tension test, okay, which is what the main aim in this particular chapter, okay, how is it generally done? Okay. So, when we speak about the tension test here, okay, or tensile test, we are speaking in terms of sheet, Okay. So, of course, the concepts are same for rods also, but sheet is a raw material here. So, we are looking for sheet here. So, how does the sample look like? It is like this. So, I have given you a schematic here. So, you can see that the sample has got two important regions. One is a shoulder region, other one is the deforming region here. Okay. The shoulder region actually goes into the clamp. So, this part actually goes into the clamp, and this part also goes into the UTM, clamp of the UTM, okay, and then it is actually held rigidly such that there is no slipping between the clamp and the surfaces. Okay. So, generally what you do is you hold it on one side and you give displacement on the other side. Okay. So, displacement will come in the x axis, okay, and depending on the material it will take a particular load to reach that particular displacement or deformation, that is actually called as P. Okay. So, this sample has got other important features. So, one after another I have written it here, but this tension test is one of the most common and simple mechanical tests to understand the deformation behavior of sheet material. This I already introduced to you, and this figure is a tensile test piece. And when we speak about this kind of dimensions, one has to refer some standards. Okay. For example, ASTM standards, EA item 22 could be one reference. There are other references also, standard references you can follow. Okay. That means what? That means this shouldered length and this radius and this distance and this L0, okay, all are fixed. Okay. It is established over several years and one has to follow that. And thickness will change depending on what material you want to test. Let us keep it as a T0. Okay. And you will see that the initial width of the deforming region is, let us say, W0. Okay. This L0 is a reference length that we are picking up. It is generally called as a gauge length. Okay. It is called as gauge length, and another dimension you have, that is T0 here. That is the initial thickness. Okay. So, this is a characteristic of a variety of standard test pieces that have parallel reduced section for at least 4 times that of width W0, but there are standards meant for that. Okay. So, now what do you do? So, your W0 is known to you because you are going to cut this. So, L0 is known to you, you are going to take this reference, and T0 depends on the material thickness, and you hold it on one side and pull it on the other side and you calculate load, and that is given by the machine itself. Okay. And the load on the specimen at any instant, that is P, is measured by load cell in the testing machine. So, UTM has got load cell that is going to give you load at each and every displacement. Okay. And the displacement is generally referred with respect to L0, which is nothing but gauge length. Okay. The gauge length is like, for example, 50 mm for you take it. So, 50 mm will become, let us say, 51, 52, okay. It will reach up to, let us say, 60, 70 or 80 depending on what material you are going to deform. Okay. Large material is good from ductility point of view, means you can extend it to a larger dimensions, larger lengths, and that change in length is generally monitored by extensometer, which is a separate device which is used to clamp it at the gauge region. Okay. You have to clamp it, okay, and you have to measure the displacement. Okay. So, the extensometer monitors a gauge length L0 in the middle of the specimen, and at any instant the gauge length L and the extension is given by delta L is equal to L minus L0. So, this delta L is called as the extension. Okay. Delta L is given by L minus L0. L is a new dimension and L0 is the initial gauge length, let us say 50. So, 51 minus 50, 52 minus 50, 53 minus 50 will give you delta L. So, this P and delta L, okay, these two are very important fellows to calculate a load displacement graph, which is the raw data that the machine can give. Okay. So, then my next slide will show you the details about load extension diagram, which I have given it here. Okay. So, you whenever you do tensile test of a typical metallic material, okay, then you will get a load and extension like this. Okay. So, load in y axis generally you can imagine that unit is in kilonewton and extension is in, let us say, delta L, which is in mm. Extension is in mm. The load is in kilonewton, you can imagine. Okay. And you all know that load generally increases, okay, and it crosses let us say yield strength, okay, that we will discuss now. So, let us say now it is Py. Py is a yield load. Okay. So, and after that you are going to enter into plastic deformation. This region you can call it as plastically deforming region or plasticity region, and it reaches P max, that is maximum load, and you will see that after P max the material is going to deform with reduction in load, and it is going to come here this way, and you will have a fracture here. Okay, it is fully fractured. The sample will become two different regions like that. Okay. So, you will see that generally fracture happens somewhere in the middle. It is expected that fracture happens in the gauge region. Okay. So, now this particular figure I already introduced, which is load versus extension diagram, and here there are some important points. As I told you, Py is called the initial yielding load at which tensile strip starts to plastically deform. Okay. Py is actually a transit region, you can imagine. Okay. So, Py is a transit region. After that it is expected to deform in a plastic manner. Okay. That means a permanent shape change. Okay. So, just after the yield starts, okay, just after the yield starts, the material undergo strain hardening. That means when you cross Py, okay, when you cross Py, you will see that the material undergoes strain hardening in this region. Okay, strain hardening. Okay, the consequence of strain hardening is nothing but load will keep on increasing with extension. The material becomes harder and harder when you extend, when you deform the material, right, because of strain hardening. Okay. And you will see that the strain hardening occurs when tensiles try to resist the deformation under loading condition. Okay. Due to strain hardening, a phenomenon that most metals alloy display, the strength or hardness of the material increases with plastic deformation. So, why strength increases during plastic deformation is mainly because of strain hardening. Of course, one can understand the mechanism more from material science point of view, but for this particular course this would be more than sufficient. Okay. So, the strength load increases with displacement in the plastically deforming region is mainly because of strain hardening. So, once you cross the strain hardening portion, you will reach a maximum load called P max. Okay. P max is the maximum load, and after that something is going to happen, or once P max is reached, something is going to happen. Okay. So, what is that? During strain hardening, the load increases to P max, which is a maximum load attained during the tensile test. Fine. So, beyond this point, strip deformation stops being uniform. So, P max is a reference for uniform deformation. P max is a reference for uniform deformation. So, any shape change that you are going to give, you should be able to give before it reaches that particular point. Okay. And whenever P max is reached, it is a hint for you that there is some sort of instability, like for example diffuse necking that has already started in the material if it has got one. Okay. A diffused neck appears in the decreased portion, and a non-uniform extension keeps occurring inside the neck until strip collapses. So, what does that mean? So, that means when P max is reached, okay, you may have necking in the material. Okay. So, diffuse necking means what? So, this is a gauge region, and the gauge region will have some sort of necking like this, okay, over a large region, okay, over a larger gauge length. You can imagine this is the gauge length, let us say. Okay. You can imagine that this kind of neck will be formed. Neck means the dimension is going to be, area of cross-section is going to be less here as compared to the other regions, as compared to the other. That indicates that the material's ductility is almost over. So, we have to be careful. Okay. So, after that what is going to happen? You are not going to stop it, you are going to pull the material apart. Then what will happen? The diffuse necking, for example, will be localized in a very small region. Okay. And then both the materials will actually split. So, you will have two different regions like this. You will have two different regions like this. This is your gauge length, let us say. This is your gauge length. Initial gauge length, what you are referred in the previous graph, is this now. Okay. So, is this now. So, that is the whole process, and you call this as a fracture here. So, Py indicates a transit between elastic to plastic deformation. Then P max, you have to be careful, one moment you reach that, it indicates that some instability like necking is started, and then further deformation will happen, but at reduction of load, because there is not much area to support that load bearing ability of the material. Okay. So, then what happens is the load will decrease with further displacement. Okay. So, the load increase here is because of strain hardening, and this load decrease is mainly because the deformation is localized in the form of necking. So, now this load displacement graph, or it is called as load extension graph, is just one stage that the material is, that the machine is going to give you. Okay. So, you will see that this load displacement graph may not be sufficient for further analysis for us. So, we introduce something called as engineering stress strain curve. Okay. The engineering stress strain curve is obtained from load extension curve by simply dividing the load by initial cross section area. This load divided by initial cross section area will give you engineering stress. We will see that formula later. Okay. So, although this had the advantage of providing a curve independent of the test piece initial size, correct. So, now same material, different dimensions are there. Okay. So, you can have a common engineering stress strain graph just by normalizing it with respect to, or dividing it with respect to initial area of cross section. Okay. So, that is the advantage it has got. Though this is the case, we are saying that it is still not true material property curve. Okay. So, the true material property curve will come in the next stage. Okay. So, now what is the actual definition of engineering stress? These are all the standard definition that probably you might have studied. I will just summarize it here. Okay. Engineering stress, sometimes is called as ES, sometimes called as sigma E and G. It is a P by A naught, where P is the load that you got in y axis and A naught is the initial cross section area. And like engineering stress, you also have engineering strain, which is nothing but in x axis. Okay. It is called as small e, or sometimes called as E and G. It is delta L by L naught. What is delta L? Delta L is nothing but the formula which you have used before, isn't it? Delta L is nothing but this fellow. Okay. L minus L naught. Okay. L minus L naught is your delta L. Okay. That delta L by initial gauge length divided by 50 into 100 will give you that in percentage. That means what? 51 minus 50 divided by 50, 52 minus 50 divided by 50, like that you can calculate it, and you will get engineering strain in percentage. You can keep it in as it is also. Okay. Where delta L is a change in length and L naught is the original gauge length. Okay. So, now here one thing is very important, that what gauge length you are going to pick up. That is why we are saying that your gauge length L naught is a reference length to calculate any strain. Okay. Any strain, if you want to calculate this reference length, what length you are going to pick up is going to be very, very important for us. Okay. And yield load we have seen. So, from yield load you can get initial yield stress. Okay. It is called as sigma F0, or it is called as sigma Ys also, and nothing but Py by A naught, where Py is the load at yielding and A naught is the initial cross section area. So, if Py is known, in the previous diagram you have seen, no, Py is known, divided by A naught, okay, as it is, will give you your sigma Y or sigma F naught. Okay. So, now by using this formula and by using engineering strain formula, you can get the engineering stress versus engineering strain graph in this way, and you will note that this particular point is nothing but your material yield strength. Okay. And this is your UTS. Okay. And this is your same fracture. Okay. So, how do you get UTS or sigma UTS? It is nothing but P max, the P max which is noted down in the previous graph, divided by A naught will give you P max, like Py by A naught, here P max by A naught. Okay. And there are two important properties other than this that is measured here, with that is nothing but uniform elongation and total elongation. Okay. This total elongation is nothing but up to fracture, whatever elongation it has got up to fracture, which is given actually in the previous graph itself. I have noted down here, it is nothing but L max minus L naught divided by L naught into 100. What is L max? L max is the gauge length once it is fully fractured, say for example 75. Okay. 75 minus 50 divided by 50. Okay. So, that is going to give you your E total, and for EU, okay, it is the same formula, only thing is you need to know what is the extension at which this EU has to be referred to. So, for that you need to know what is UTS and the corresponding your the length of the sample. Okay. So, that length, okay, minus L naught divided by L naught, that will give you EU. So, uniform elongation is the elongation at maximum load. Okay. Or what you can do is like, since you are already converted everything to engineering strain, already you are converted, so the corresponding strain is nothing but EU. That is what is written here. Okay. So, from here to here, what you call is nothing but EU, but up to fracture, full fracture if you refer, that is called E total. That is nothing but total elongation, and this is nothing but uniform elongation. So, for most of the material, this is important, E total minus EU, this distance, okay, E total minus EU, that is nothing but this value, this is going to be very, very crucial. Okay. So, now some other known properties you can get, for instance, you can get yield strength, okay, that we have already indicated sigma y as yield strength, but sigma y is generally not obtained by this formula, because here Py is also not known to us. Okay. Practically, sigma y is evaluated by a method called as a proof stress evaluation. Okay. But before that, you know how to get Young's modulus of the material. So, it is nothing but your yield strength divided by Ey. The slope of elastic part of the curve is nothing but elastic modulus, also called as Young's modulus. So, you know how to calculate it. Okay. And in some materials, what happens is the transition from elastic to plastic deformation is going to be unclear. Okay. So, there will be a smooth transition. There will be a smooth transition from elastic to plastic. So, in that type of materials you have to be careful, and for calculating the yield strength, and for that we are going to use this particular method. So, what we do here is you zoom in to the initial part of the deformation, initial part of the curve, engineering stress strain curve, which is what is given here. Okay. You will see that in the engineering strain x axis you pick up 0.2% strain, assuming that engineering strain is given in percentage. Okay. You pick up a 0.2% strain, and then you draw a line parallel to the elastic part. Okay. So, wherever it is going to hit the curve, the corresponding one, you can call it as a sigma y. Okay. So, in this kind of instances where the transition is going to be smooth, you can use proof stress. This is the stress required to create a specific tiny plastic strain, typically 0.2% or roughly twice that of elastic strain at yield. Okay. This is elastic strain at yield, no? Elastic strain at yield, no? So, maybe twice than that of that, that is what is referred, but otherwise generally standard says that 0.2% strain you pick up, and then you go and hit it in the stress strain curve. The corresponding one is nothing but yield strength. As shown in the figure, proof stress is calculated by drawing a line parallel to elastic loading line offset by specified amount. This much amount you are doing. Okay. So, this is nothing but your yield stress evaluation. Okay. So, now given a load displacement graph, we can get engineering stress strain graph, and we can get yield strength from there, UTS from there, uniform elongation, total elongation, all those things can be evaluated. Okay. And of course, Young's modulus can also be evaluated, which is nothing but the slope of the elastic part of the deformation. So, now we are going to convert this engineering stress strain graph into true stress strain curve. Okay. And this true stress strain curve is predominantly used for any engineering analysis. Okay. So, one issue with the engineering stress strain curve is it is based on initial dimensions of the test piece, right. So, now if you want to really get the real picture of the deformation, then one has to have some curve which is depending on the instantaneous dimensions, okay, which is nothing but your true stress strain data or true stress strain curve. Okay. Since metals and alloys can deform plastically without significantly changing their volume, the true stress can be calculated from the load extension diagram using the rising portion of the curve, that is nothing but your plastic deforming region between the first yielding and the maximum load. Okay. So, what we do is we will define true stress and true strain, and that can be obtained from the load displacement graph or the engineering stress strain graph, okay, and mainly in the plastically deforming region. Okay. Say this part, okay, you pick up this part of the region, okay, and you can get a true stress strain curve, which is what is shown in this diagram. Okay. You can see that your y axis is true stress, unit is same, megapascal. Okay. So, true strain you can keep it in percentage also, and you will see that the graph starts here and it keeps on increasing. Okay. So, you will see that there is always an increasing trend. Okay. That is the main difference between elastic your engineering stress strain graph and true stress strain graph. Okay. And this part is your sigma f naught, which is nothing but yield strength, and this is nothing but a uniform elongation. We have drawn up to that only. Okay. Of course, true stress data can be obtained beyond that also. Okay. But this curve is drawn only up to your uniform elongation, that is up to UTS. So, yield strength to your UTS part. You are converting into true stress strain data. Okay. So, now what we are going to do is we are going to define what is true stress, that is nothing but sigma. So, engineering stress we referred as ES, engineering strain is referred as I think E, okay, and here true stress we are actually referring it as sigma. So, sigma is nothing but P by A. So, A naught is the initial area of cross section, but A is nothing but instantaneous cross sectional area or area of cross section. Okay. So, P is actually given by the load displacement graph, okay, but how do you get A? Because A is going to be changing with the deformation. So, for that what you are going to do is you are going to pick up this particular important equation. Volume of the gauge region is considered constant in plastic deformation. Okay. So, we know that it is A naught L naught will be equal to AL. So, A naught L naught will give you initial picture of the sample or initial size, and AL is going to be instantaneous one. Okay. So, A naught is known to you, okay. L naught is 50 mm, okay. A naught is known to you. A naught is nothing but, let us say, area of cross section is nothing but your width into thickness. So, width of the sample is known to you, W naught, which is known to you, and thickness is known, let us say 1 mm. Okay. So, we can get initial volume, and A is the one which you are going to evaluate, and L is nothing but your instantaneous length, which is also known to you, okay, which is also known to you, okay, because you are the one who is going to deform. Let us say 50 mm gauge length will become 51, 52, 53. So, you know the length. So, from this A can be obtained, and I am going to substitute here. So, A is nothing but A naught L naught divided by L, which I will keep it here, which is nothing but P by A naught into L by L naught. A naught L naught by L, so L goes to numerator. So, PL by A naught L naught is going to be your sigma. So, I can get true stress now, because P is known, A naught is known, L naught is known, L can be calculated at every each and every level of deformation. So, I will get it. So, now when it comes to true strain, it is generally represented as epsilon, generally represented as epsilon. So, epsilon is nothing but integral d epsilon, you can say. For small deformation, d epsilon can be written as dl by L. Okay. So, if you integrate it from L naught to L, okay, where L naught is your initial gauge length or reference length, and L is the length of the instantaneous length of the gauge length, okay, or the final length at which fracture happens, whichever is the reference for you. Wherever you want to calculate, you can calculate it. So, L, it will give you ln of L by L naught, where L is your instantaneous length, gauge length, and L naught is your initial gauge length. Okay. So, this is also known to you, because L is known to you here itself. So, the same L will come, and L naught is, let us say, 50 mm. Okay. So, now you have sigma and epsilon. So, you have load, then you have delta L curve. Okay. From there onwards, you can directly get sigma versus epsilon. Okay. That is one way. The other is another way also. PL, say you can get SE. Okay. That means engineering stress, engineering strain. From there also you can get sigma epsilon, which is what is given here. So, you need to relate engineering stress and true stress, engineering strain and true strain, which is what is given in this particular discussion. So, we know the sigma is equal to P by A, which is nothing but P by A naught by A naught I am keeping. So, A naught will be cancelled, P by A will remain. So, it is correct. So, what is P by A naught? Nothing but my engineering stress. Yes, A naught by A. A naught by A would be equal to L by L naught I am keeping. So, L by L naught will remain same. Fine. So, now engineering strain, I will come back to this formula. So, engineering strain is nothing but L minus L naught divided by L naught. That also we have seen already. Delta L by L naught we said. We said delta L, this is nothing but delta L, no? Delta L by L naught we said. So, nothing but L minus L naught by L naught, which is nothing but L by L naught minus 1. So, L by L naught is nothing but L by L naught is nothing but 1 plus E. Okay. So, I am going to put 1 plus E here, okay, and I will get sigma is equal to S into 1 plus E. Okay. Sigma is equal to S into 1 plus E. So, here you will see that if I do not want to evaluate sigma versus epsilon graph directly from load displacement graph, then I can use this route also. So, first you calculate engineering stress and engineering strain with the usual procedure described before, and using this formula sigma is equal to S into 1 plus E, I can get sigma. Similarly, what I can get is epsilon also. So, epsilon is nothing but ln of L by L naught. So, L by L naught is nothing but 1 plus E. So, epsilon is equal to ln of natural logarithm of 1 plus E. Okay. So, this will give me my sigma versus epsilon graph, which looks like the one I have written before. Okay. This is nothing but sigma, you can say nothing but epsilon. Okay. It will look like this. Okay. But one has to be very careful in using these equations because we do not know how accurately you are going to measure once the necking starts. Okay. After Pmax or after UTS, you have to be careful in evaluating the dimensions because necking is going to happen. One may not measure the dimensions accurately. So, you have to use these equations, these calculations suitably. Okay. So, but this is an important thing. So, here I will again tell the nomenclature. Here sigma is nothing but true stress, S is nothing but engineering stress, E is nothing but your engineering strain. Epsilon is true strain, E is engineering strain. So, we are going to use this sigma S E, okay, and epsilon, sigma epsilon S E in this fashion only. Okay. So, now then comes how do you relate stress and strain. Okay. So, in the elastic part of deformation, we know Hooke's law, sigma is equal to E into epsilon, which is going to be useful predominantly to describe the stress strain relationship, where E is nothing but your Young's modulus, through which you calculate Young's modulus before. Okay. But beyond that, okay, this equation has to be modified, and there are several equations of that type. We will see a little later on what is it. One important is basically power law. Okay. This is an important equation, sigma is equal to k epsilon power n. This is like a power law, y is equal to ax power b type. Okay. So, where sigma is nothing but your true stress, again epsilon is going to be true strain. Okay. We have to be careful in this. Okay. Again I am saying sigma means true stress, epsilon means here true strain only. Okay. So, now this k n n actually is going to vary depending on the material. Okay. So, different material may have different load displacement graph and hence a different stress strain graph. So, unless otherwise you do something to the material, it is not going to change. So, stress strain graph is going to be a material property. Okay. You do something to the material, then it will change, otherwise no, it is not going to change. So, which means that this k and n are nothing but material property of this particular available in this equation. Okay. And this one way to evaluate is basically to take a logarithm on both sides, and you will get ln of sigma is equal to ln of k plus n is power. So, it comes front n ln of log of epsilon. Okay. So, and this you can easily understand is of the form y is equal to mx plus c, where c is this fellow and your m is nothing but your n. So, and this k and n has got a specific name, and we are going to use this predominantly, this particular equation predominantly throughout the course. So, one should remember this, where n is called as strain hardening index, okay, sometimes called as strain hardening exponent, and k is called as strength coefficient. K is called as strength coefficient. Okay. And again sigma is true stress, epsilon is true strain. So, k is strength coefficient, n is strain hardening index or strain hardening exponent, you can say. So, how to get this now? So, now you are converted into a straight line plot, okay, where this is your y and this fellow is your x. So, I am going to draw x versus y, where y is your log sigma and log epsilon you can take, and you pick up the stress strain data only in the plastic deforming zone, that is between yield strength and UTS, okay, and you convert all that sigma epsilon into logarithmic plot like this, okay, and you will see that generally you get a straight line fit like this, but not all materials will show one straight line, okay, but generally most of the materials show this one straight line like this, and slope of this curve is given by n. Okay. If you take slope of this, then it will become n. So, you will get one particular value here, okay, and the intercept of that will give you k, and the intercept of that will give you k. Okay. So, in this way one can get k and n. Okay. So, what you do is basically you convert a power law into a straight line fit, and the slope of that curve will be given by n, okay, or in other words slope of that curve gives n, okay, which is nothing but the strain hardening exponent, and the intercept in a way will give you k. And here I have clearly written that it is only in the plastically deforming zone. Okay. So, this way one can get k and n, and you will see that once you have a stress strain behavior, okay, true stress strain behavior done. So, you have load displacement graph, from that you have S versus E engineering stress strain graph, from there you get sigma versus epsilon true stress strain graph, true and stress and true strain are related by this particular simple power law sigma is equal to K epsilon power n, which actually describes the strain hardening part of the curve. Okay. This power law is nothing but the one which describes the strain hardening part of the curve. Okay. And this you are converting into this particular plot, okay, and you are going to get K and n in this fashion which I told. Okay. So, now the accuracy of calculating K and n depends on how good the fit between the sigma versus epsilon graph that you get from this equation and the original true stress strain curve. Okay. So, let us say you have true stress strain data that you obtained from experiments in this route. Okay. In this route you got it. Okay. Now, what you have done is nothing but you are fitting the true stress strain graph into this equation. Okay. Let us say, for example, you are calculating this equation as, let us say, sigma is equal to, let us say, 200 epsilon power 0.25. Okay. We will see several such equations in the problems. Okay. You will get some flavor. Okay. Sigma is equal to 200 epsilon power 0.25, where epsilon is going to be changing. Accordingly, sigma is going to change. Okay. So, if you have accurately calculated this 200 and 0.25 or K and n, then your true stress strain data from the experiment and this equation is going to match. So, it is all about fitting the stress strain data that you get from experiments using this type of equation. Okay. So, now you will see that from a tensile test you are going to calculate this type of evaluate this type of equations, but actually tensile test you will see that the material is going to fail at one particular strain, but in actual sheet forming operations may undergo large deformation where strains can be much larger than the strain that you see in tensile test. Okay. So, in that region of deformation, okay, where you do not have data, what you can do is you can use this equation extrapolate. Okay. You can extrapolate this equation and you can use it and relate sigma versus epsilon, okay, and relate sigma and epsilon beyond tensile test also. Okay. Otherwise, you do not know how to extend it beyond your true stress strain data that you get from experiments. If you want to extrapolate it, you need some form of equation, right, and this fit equation will give you that, okay, predominantly in the extrapolated region. Okay. So, now this completes the tensile test part. You know how to get different properties, K and n, everything you know how to get it. Okay. We will work out some problems, things will be clear. So, other than that, there is one more important property of the material called as anisotropy. Okay. So, this anisotropy you will see that is a very important property predominantly for sheet materials. Okay. So, isotropic materials have identical qualities evaluated in all directions. Okay. Suppose you take a sheet, okay, you take a sheet, okay, and you know that the sheets are actually rolled sheets, right. So, it undergoes prior deformation when it comes to actual applications, right. Because of this rolling, okay, the properties can change with respect to rolling directions, and that is quantified by something we define as anisotropy of the material. Okay. Anisotropy of the material means okay, the properties, okay, will differ when tested in specific directions, such as, let us say, rolling direction, transverse to that, and at 45-degree direction to rolling direction. Okay. This deviation is generally referred to as planar anisotropy. So, we are going to define it with a simple formula in the next slide, which will make us to understand it very easily. Okay. So, when you go to industrial sheets level, which are actually rolled sheets, then quantifying this anisotropy is going to be very, very important, which are nothing but you take a tensile test sample and do tensile test like the way we described in rolling direction, along the rolling direction, or transverse to the rolling direction, or 45-degree to the rolling direction, their properties are going to be different. Okay. So, now there is one more point. The average of the properties in the plane of the sheet and those in the through thickness direction may also differ from one another. That means on the plane, suppose this has got a sheet, okay, the sheet plane, okay, and in the through thickness direction, okay, what are the properties in the through thickness direction? They are also not going to be same, they differ. Okay. So, now how to quantify this anisotropy in sheets, okay, and then we define something called as a plastic strain ratio called as R, okay, which is typically used to represent condition of anisotropy in materials whose characteristics vary with the direction. So, here we are specifically speaking about rolling direction. Okay. Let us say this is your rolling direction, we are calling it as RD, perpendicular to that is TD, okay, and in the through thickness direction is in this way. Okay. And 45-degree direction means in the plane itself this is 45. One can go for other discretization also, 0, 30, 60, 90, that way also one can go. The simplest way to divide that is 0, 45 and TD or 90 degree. Okay, so how do you define this R? It is generally referred as capital R or sometimes referred as small r also. So R is defined as, or plastic strain is defined as the ratio of width strain to thickness strain. Okay, R is nothing but epsilon W by epsilon T. As we said in the previous slide, epsilon means true strain, so which means its width strain, that is true quantity, divided by thickness strain. Okay. So to further to calculate, this is true strain, so it is nothing but ln of W by W naught, where W is instantaneous width and thickness instantaneous thickness, ln of T by T naught, okay, which is nothing but ln of W by W naught, and T by T naught can be written as W naught T L naught divided by WL. Okay. So we are saying that W naught L naught T naught would be equal to WL T. So you need T by T naught, right? So T by T naught will give you, T would be WL, and here you have W naught L naught. Okay. So of course, if you do not want this requirement, you can still stay with this stage of equation. So true width strain divided by true thickness strain. It means, suppose if these two strains are equal, when you go for deformation, suppose you take a strip of sheet and then you deform it, okay, you will see that these two strains are equal. That means R is equal to 1. What does that mean? That means in width direction and thickness direction you have almost same strain, which means the material is supposed to be isotropic in nature. Any deviation from this or not equal to 1 will tell that material is anisotropic. Material is anisotropic in nature. So R can be less than 1 or greater than 1 depending on the material. Okay. So now how do you calculate this R? There are standard procedures for this. I described it here. Okay. So of course ASTM standard, this number is also provided here for the sample. So what we do is a very simple test like tensile test only. So here what you do is you take a rectangular sample, a typical dimension. You can say this is 175 mm, this is total length, this is 28.58 mm. So you can refer to this ASTM standard. And at the geometric center of the sample, you will put this indents. This is 20 mm and this is 20 mm indents you put. Okay. And then what do you do? It is the same UTM on which you would done tensile test. You hold it on one side and you pull it on the other side, give some displacement. You have to stop the test. So when is it? In the tensile test, actually you stopped it until fracture. It has to fully fracture. But here you stop it at 15% strain, okay, at 15% of this 20 mm. 15% of this 20 mm. So what do you do here is R value measurement are taken at a strain equal to 15%. Okay. So what do? You can calculate 15% of 20 mm, okay, and add it to 20 mm, okay, this 20 mm length, because length is a measure which you can control. Okay. Let us say for example that has become, let us say 23 mm or 24 mm like that. Okay. So then what do? You stop the test at that particular instant. So you know the new length, right? You know the new width, right? Length will increase, width has to decrease, and accordingly thickness will also reduce in this particular location. So with the change in this length, with change in width and change in thickness, you can calculate all the three strains, isn't it? You can get epsilon L, you can get epsilon W, and you can get epsilon T. And what is the formula for R? R is given by true width strain divided by true thickness strain. So you need only this strain and this strain, which you can get it by measuring it. With the microscope you can measure the new width, that will give you epsilon W. With micrometer, okay, or a screw gauge, sharpened screw gauge, pointed screw gauge, you can get the thickness at maybe 5 different locations and you can get new thickness, take an average, that will give you epsilon T. Okay. So from this you can get R value. Okay. So then you will feel that, okay, R is let us say 1.3, the material is anisotropic. R is let us say 0.85, material is anisotropic in nature. Okay. So now this R value can be calculated in 0 degree rolling direction, we call it as R naught, along 90 degree rolling direction, that is R90, and along 45 degree rolling direction, that is R45. Okay. So in that way it can vary with several such angles are there, isn't it? So one has to have some averaged quantity which is actually given by R bar. Okay. So this R bar is nothing but average plastic strain ratio. It is also representing something called as normal plastic anisotropy ratio, which is generally given by R naught plus R45 plus R90 plus 2 R45 divided by 4. So you calculate R naught, you have to test it separately. 2 width strain divided by 2 thickness strain. You do separate test again in this direction, so you will get 2 different thing. In 45 degree direction again you get epsilon dt. So now you have 3 values, right? Substitute in this formula, you will get a R bar. Okay. So one has to be little bit careful when you divide this equally. So it is not mandatory that you have to divide it only at 45 degree intervals. You can also divide in other intervals also. Let us say 0, then you have 30, okay, then you have 60, then you have 90. Okay, so otherwise you can have 0, 15, 30, 45. Okay, then other angles up to 90 you can calculate. So accordingly you have to change the formula. Formula is not going to remain same. One has to be careful. Okay, and in the plane of the sheet, how R value is changing, that can be referred with respect to planar anisotropy, okay, which is given by delta R. Delta R is nothing but R0 plus R90 divided by 2 minus R45. Otherwise, you can also write R0 plus R90 minus 2 R45 divided by 2, okay, where R0, R45, R90 are plastic strain ratio in rolling, diagonal and transverse directions. Okay, this delta R can be positive or negative in nature. This is an average value, so generally it is an average quantity of R0, R45 and R90. Again, one has to be very, very careful in using this formula for different sets of rolling directions, which I have referred here. This is valid only for 0, 45, 90 degree rolling direction. Okay, so one has to look into it. So now, given a sheet, you can get R value, and then you can get R bar, and then you can get delta R. Okay. So what is the use of this R bar, delta R, all those things we will see in the next lecture. And just to summarize what we have seen today, I introduced a sheet forming process. Okay. So variety of sheet forming process we have briefly discussed. Some of them you will see elaborately in the next future classes. Okay. And after that, predominantly we discussed about a tension test, okay, which is very mandatory for any characterizing any sheets. And that is also used to model the sheet deformation. Okay. So we started with how to get load displacement graph in UTM, and then converting that to engineering stress strain graph, and then to true stress strain graph. So true stress strain graph, we said sigma epsilon graph is the main data that we need. So how to fit the true stress strain data in the form of an equation, let us say power law, sigma is equal to k epsilon power n, where n is the strain hardening exponent and k is the strength coefficient. If a fit is accurate, then experimental data and the data from the equation is going to be agreeing well. Okay. Then I discussed with you briefly about anisotropy, how to calculate the sheet anisotropy, which is generally created by rolling operation. Okay. Then you refer something called as R0, R45, R90 with respect to rolling direction, where R0 is along the rolling direction. And then we defined a parameter called plastic strain ratio, or a property plastic strain ratio, which is defined as 2 width strain divided by 2 thickness strain. And how to calculate R for material is also described with simple testing procedure, which is shown in this figure. Okay. So from there onwards, we introduce something called R bar, which is like an average quantity, and then delta R, which is going to tell you how different is R value in the plane. Okay. So R0 plus R90 by 2 minus R45. So you take an average of R0 and R90 and you compare that with R45, how different they are. That will be given by delta R. That is called planar anisotropy of the sheets. Okay. So with this we will stop, and then we will see in the next class.